Alright, hello everybody. In this video we are going to be drawing individual atoms of elements from the periodic table, and then we're going to take a look at some ionic bonding and some covalent bonding. So to start this video off, we're just going to remind ourselves of the basic atomic structure. And you saw this by looking at the PowerPoint video, but we basically reminded ourselves that we've got protons and we've got neutrons that are going to sit inside the nucleus, the center of that atomic structure. And then around that, we're going to have these shells of electrons that are going to be in orbit around the nucleus. And in this class, we're going to be talking about molecules that basically are going to be large enough where we're going to talk about 3 shells around the outside of these atomic nuclei. And the rule that we're going to have to remember will be a little bit easier if you do, is that this rule where that first orbit that is around the atomic nucleus is big enough to hold 2 electrons, and the next 2 shells or orbits are going to be big enough to hold 8 electrons. And this outermost shell is what we're going to call the valence shell. We can just make a mark here that the numbers represent the max number of electrons. Alright, now as we move up, let's look at some examples of trying to draw individual atoms off the periodic table. Let's just start off with carbon. So we've got carbon here. If you look at your periodic table of elements, you'll see that carbon has got an atomic number of 6, so we know that it's got 6 protons and it's going to have 6 electrons. And we know protons have a positive charge, electrons have a negative charge. If we want to write out the number of electrons in reference to, just to jump back up here, in reference to the number of electrons that can fit in each shell, we can kind of bracket it out like this. For shorthand, that first shell we know holds 2 electrons, and carbon has 6, so it's got 4 more to go here. So 4 are going to end up spilling over into this second shell. And as you remember from the rules above, that second shell can hold as many as 8, and we've only got 4 in that outermost shell. So carbon is going to be looking to react with something. And whenever we try and draw this, we can typically draw carbon, just to scoot up a hair, we can typically draw carbon in a way like this, where we've got C kind of representing the carbon, and the only shell that we need to draw is that outermost shell that determines how this molecule is going to, or this atom is going to react. So remember, we've got the 4 electrons there. When we try and fit that into orbit around this carbon, we can see again not a complete full shell, so it's going to be looking to react with something to complete that shell. Let's look at another example. If we move over a hair, the next example is going to be oxygen. And if you look at your periodic table of elements, you can see oxygen is one of these elements that has an atomic number of 8. So you've got 8 protons, we've got 8 electrons. If you want to do the little quick reference there, we've got 8 electrons to dole out. We know 2 are going to fit in that first shell. As many as 8 can fit in the next shell, but we've only got 6 to go in there. So once again, that outermost shell could hold 8. We've only got 6. Oxygen is going to be looking to react with something. So if we try and draw oxygen, again, just that outer shell is what we need to draw. It's going to determine how this atom is going to react with other things. And in this one, we can fit 1, 2, 3, 4, 5, 6 of those electrons, so almost full. Next example that we saw was of sodium. So when we look at sodium in that periodic table, we can see that it's got an atomic number of 11. So we've got 11 protons and 11 electrons. Doing our quick little breakdown of the number of electrons, we know 2 can fit in that first shell, 8 can fit in that second shell, and now we've got one more to dole out, and it makes its way into that third shell, which we know from the rule before can hold 8, and we've only got 1 there. So when we go try and represent this, when we draw sodium, we need to make reference to the fact that that outer shell has just 1 electron. So sodium is something that's highly reactive. It's looking to do things to either typically get rid of that extra electron so that it would have a complete outer shell. We'll see that in just a second when we draw some chemical bonds. Last example that we saw here is going to be of fluorine. And if you look, fluorine has an atomic number of 9, so we've got 9 protons and we've got 9 electrons. From our rule, we know we've got 9 electrons to pass out, so 2 can fit in that first shell. 8 can fit in that next shell, but we've only got 7 to pass out. So once again, we've got an outer shell that's not completely full. We should be able to represent that by drawing this. And again, there's the F for fluorine, and this valence shell we need to represent has 7 electrons. So 1, 2, 3, 4, 5, 6, and 7. It's almost full, so it's going to be looking to react with something as well to get a completely full shell. Okay, switching gears to talk about ionic bonds. We'll remind ourselves from the PowerPoint that in ionic bonds there is a transfer of electrons, so one atom is going to gain an electron while another atom is going to lose an electron, and that's going to throw off the balance between protons and electrons. So one of these atoms is going to end up with more protons and thus a positive charge, and the other atom is going to end up with more electrons and thus a negative charge. The two examples we're going to see here is of sodium chloride and magnesium oxide. So first example that we see here is going to be of sodium chloride. And if we take sodium chloride, let's break these two individual atoms down. We know that sodium over here has an atomic number of 11, so we've got 11 protons and 11 electrons. Chloride over there has got an atomic number of 17, so it's got 17 protons and 17 electrons. If we do our little bracket there, we know we've got 11 electrons to pass out here. 2 fit in that first shell, 8 fit in that second shell, and then we have one more to pass out there, and so just one spills over into that third shell. And when we draw that, like we just saw, it's this outermost shell that just has 1 electron. We can represent that by drawing our sodium and that outer shell with just its single electron. Moving on, let's look over here at the chloride side. And here we've got an atomic number of 17. That means 17 electrons. And if we go to pass out those 17 electrons, we know 2 can fit in that first shell. 8 can fit in the next shell. And so now we've got 7 more to pass out. So that outer shell, once again, is not completely full. It's in a situation where it's looking to either gain or lose electrons to get completely full. And when we diagram that out, remember we would do something like this where chloride has 7 electrons in this outermost shell. One thing that we'll see that happens here is sodium can just kick off this electron. Donates an electron over to another atom that might need one. So we've got a transfer here of an electron. So down here we've got sodium, and now we can draw it with its outer shell completely full of electrons. And when we remind ourselves of the math down here, it still has 11 protons, but since it's lost an electron, we only have 10 to pass out. So if we do our little bracket once again, we can see that 2 electrons fit in that first shell. We know that 8 electrons fit in that second shell, and that's all that we have to pass out. So this now is completely full and what we consider happy, even though the number of protons now outnumber the number of electrons. So we would have to draw it with a plus sign there. Over here looking at chloride, we now can draw it with its outer shell completely full after it's picked up an electron. but we have to go back and do the math. It still has 17 protons, but now in terms of electrons, it's picked up one, so it's got 18. And when we do our brackets again, we can still see that 2 electrons fit in that first shell, 8 electrons fit in the second, and we know 8 fit in the third, and that's all we have to pass out. So its outer shell is completely full. This molecule is happy, or this atom is happy, but we have to go back and remind ourselves that it now has more electrons than it has protons. So overall, one more negative charge than positive charge. And it's these opposing charges that, like the force of a magnet, are going to pull these molecules or these individual atoms together, forming an ionic bond and a molecule. In our last example of an ionic bond, we've got magnesium oxide. And if you look at the periodic table of elements, you're going to see magnesium has an atomic number of 12. So that means 12 protons and 12 electrons. And we know oxygen has an atomic number of 8. So 8 protons and 8 electrons. When we do our brackets real quick, we know that we've got 12 electrons to pass out. 2 fit in that first shell, 8 fit in the second shell, and we've only got 2 more to pass out there. So again, this magnesium, its outer shell is not completely full. It's got 2 electrons in its outer shell. Looking at oxygen, we can see 8 electrons to pass out. Again, 2 in the first shell, and we've only got 6 more to go. So 6 are going to spill over into that outer shell, leaving it not completely full, looking to react. How we diagram that, the magnesium, we can draw its outer shell, and the thing to note is that it's got just 2 of those electrons in the outer shell. And oxygen over here, we can see it has 6. And in this situation, we're going to see an ionic transfer of electrons where 2 of these electrons are going to be lost. So in this transfer of electrons, we're going to end up with a magnesium. Let's scroll up here a little bit. After it loses those 2 electrons, we now can draw an outer shell that is completely full, because we can do the math. It has lost 2 electrons, so its number of protons is still 12, but the number of electrons has now dropped from 12 down to 10. So when we do our brackets, again, 2 electrons can fit in the first shell, 8 electrons can fit in the second shell, and that's all that we've got. So this thing is completely full in its outer shell. It's happy. However, when we look at the number of protons and electrons, it's got 2 more positive charges than it does negative charges. So this is sometimes where you see the 2+ there. So magnesium is a positively charged ion, something that we're going to call a cation ion. Oxygen, on the other hand, if we see what's going on here, let's draw oxygen. It's in a situation where it has now picked up 2 additional electrons. So going from 6 in its outer shell to a full 8. But once again, we have to do our math again. It's still got 8 protons, but in terms of electrons, it's now picked up 2, so it's gone to 10. We know when we split those out, 2 in the first shell, 8 in the second shell, so now its outer shell is completely full, and it's happy. However, it's got more electrons than protons, in fact 2 more, so those negative charges are going to win out. You can see this as an anion. And again, we're going to have an ionic bond form between these 2 atoms, forming a nice chemical bond. Okay, so we're going to switch gears here and look at the last type of chemical bonds, which are covalent bonds. And we remember that covalent bonds are a case where there is a sharing of electrons. So this is a little bit more of an intimate type of chemical bond, stronger than an ionic bond. Let's look at some examples of these molecules that we can see here, all held together by covalent bonds. We're going to look at examples of hydrogen gas, chlorine gas, methane, there's ammonium, there's water, we've got oxygen, and we've got nitrogen. Oh, that would be oxygen gas and nitrogen gas. So let's look at these one at a time. And our first example of covalent bonded molecules is going to be one of hydrogen gas. And this is a case where we're going to have 2 hydrogen atoms and they are going to be sharing electrons. So if you look at the periodic table of elements, you can see that hydrogen is in the first column, meaning it is going to have an outer shell of just a single electron, which I can represent with an X here. And there is one more hydrogen atom, and it's also going to be close by, even though I haven't drawn those circles perfectly. I'm going to draw this second atom with its electron as a dot. And I'll just kind of draw it in this overlapping area, which is a space where these two atoms can share an electron. So they're kind of close together, and what we can see here is that from the perspective of this one atom here on the right, its shell here, its orbit has access to 2 electrons, so it's now happy. And then this hydrogen here on the left, it also has access to 2 electrons, so it's happy. This sharing of one pair of electrons is what we call a single bond. Next example that we see is going to be of chlorine. So this is a situation like we saw with hydrogen, where we're going to have 2 atoms that are going to be sharing electrons. And if you look at the periodic table of elements, you'll notice that chlorine is going to be in group 7, so it's the far right side of the periodic table. If we draw one of these atoms as an example, we're going to see that its outer shell is going to have 7 electrons. So we'll put 1, 2, 3, 4, 5, 6, and then 7 there. And there's 2 of these, so let's put another one of these chlorides here. And this second one is going to have 7 electrons as well. I'm gonna mark these in an X so that just we can have a distinction between the two. So I've got 1, 2, 3, 4, 5, 6, and then here's its 7th one that it's kind of bringing in this shared area. So again, 1 chloride over here on the right, 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell, but now it has access to 1, completing its outer shell that it's sharing with the chloride on the left. And the same thing we can say about this chloride on the left. Its outer shell is now complete since it has access to the 1 electron being shared with the chloride from the right. So our next example here of a covalently bonded molecule is going to be of methane gas. And in methane gas, we're going to see a situation where we have got a central carbon. Let's just draw that out there. And we're going to see 4 other molecules interact with it here, and each one of these 4 molecules is going to be a hydrogen. I'm going to draw these hydrogens with their single electron as an X in this shared area. So they're each bringing their own electron, and what we know about carbon is it's got 4 electrons in its outer shell, and I'll represent those 4 the 4 electrons from carbon with a dot. So now that we've got all of those filled in there, you can see that from each individual hydrogen's perspective, it has access to 2 electrons. So each one of those hydrogens are happy. And from the carbon's perspective, since it gets to share a electron from each one of those hydrogens, its outer shell now has access to 8 electrons, so it's happy. Next example of a covalently bonded molecule is going to be of ammonium. And we can see this with a central nitrogen here. And around the central nitrogen, we're going to see 3 other molecules, 3 other hydrogen molecules. Let's just label each of those with an H. And like last time, I'll draw these hydrogen atoms with their electron as an X, and I'll put it in this little shared space here. So that's the electron that each hydrogen is bringing to share. Nitrogen, we can see that it's got an atomic number of 7. So when we look, it's got 5 electrons in its outermost shell. I'll put those down as a dot here, so we can put 1, 2, 3, and then 4, 5 right there. So with these 3 hydrogens around it, that nitrogen is completely happy. It's got access to 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outermost shell. 3 of those it's sharing with the hydrogen. You can see that each hydrogen is now completely content because it has access to 2 electrons. Next example that we're going to see is going to be an example of a water molecule. So H2O here, we've got 2 hydrogens and we've got an oxygen. Here I'm going to start with an oxygen in the center. and I'm going to draw two other circles here interacting with it, and each one of those circles represents a hydrogen. We've been writing the hydrogen electrons as a tiny little x in this shared space, so that's the electron that each hydrogen is bringing. And each oxygen, if you look at the periodic table of elements, you see that it's got an atomic number of 8, so we know its outer shell has 6 electrons. We can go 1, 2, 3, 4, 5, and 6. So we've kind of put 6 of them out there. If we count up the number of electrons that oxygen has access to now, we can see it's got 1, 2, 3, 4, 5, 6, 7, 8. So it's completely happy. Each hydrogen is happy because it has access to 2 electrons. So once again, we've got a happy molecule here. Moving on. Next example that we're going to see of a covalently bonded molecule is going to be of oxygen gas. So here we've got just 2 oxygen molecules, and let's start by drawing these 2 big overlapping circles here. Each one represents an oxygen, and what we know about oxygen is that it's one of these atoms that has 6 electrons in its outer shell. So let's just put those 6 in here. The one on the right, I'll use the dots like we've been using. So we'll go 1, 2, 3, 4, and then 5, 6 in this shared space. And the one on the left, I'll use the X's since it's the only other molecule that we have here, so we can make a distinction. We'll put 1, 2, 3, 4, and then in here we'll put 5, 6. So again, each oxygen here is only able to come up with 6 electrons, but together, when they're this close, we can see that the oxygen on the right and the oxygen on the left each have access to 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So they're both content and happy. However, what we're seeing is that there are, in this case, 2 pairs of electrons that are being shared. This is what we're going to call a double bond, just because we've got 2 pairs of electrons being shared. One example here, we're going to draw nitrogen gas. And in nitrogen gas, we've got just 2 big circles to draw. Each one represents a nitrogen molecule. And we know in nitrogen there are going to be 5 electrons in the outermost shell. I'll just use dots to represent the one on the right. I'm going to fit 1, 2, 3, 4, 5. So the one on the right has got 5 of these electrons here in its outermost shell area. The one on the left I'll draw 5 as well, but I'll just use these X's. So we'll put 1, 2, and then 3, 4, 5. So the one on the left here has also come up with 5 of these electrons in the outermost shell. And when they're close together like this, we can see that there are now 1, 2, 3 pairs of electrons that are being shared between these 2 nitrogen molecules. This is what we're going to call a triple bond. So typically, the more of those electrons that you share, the stronger of a covalent bond it'll be.